first sheet. Well, Fernando introduced me as being from KEMA, and for those of you who do not know that yet, KEMA is part now of DNVGL as of last December. So I have changed jobs, but my company has merged with another company. So today's webinar is on replacement criteria for distribution transformers. A question that I often get is, when do I replace this transformer? And actually, what the person then means is, how old can a transformer get? And when should I replace it? This is a question which is not so easy to answer, especially if you take into account that most transformers are not being replaced because they are of a high age, or because they are not functioning because of their high age. So there must be other reasons why transformers are being replaced. Transformer replacement actually is an asset management decision. And asset management decision is a risk-based decision. It does not only look at age, it does not only look at failure probability, it's more complex than that. So what I would like to take you through today is a short introduction of modern asset management, and then go to transformer lifetime related issues, and see what are the different mitigating options if we are dealing with transformer lifetime issues. What is the decision-making process? And from that, I will then come to the decision-making criteria, the transformer replacement criteria, and pose some conclusions, which, if you have listened carefully, were already summarized by Fernando. I will try to substantiate that with some arguments. The contents of this paper was also published in last year at a CGRE meeting in Zurich, Switzerland. So let me first tell you a little bit of background on this issue. If we look at trends in transmission and distribution of electrical energy, then we see that the society increasingly depends on energy supply. We cannot imagine where we would be without electrical energy. A second trend is that as a result of all the investments that we did in the 60s and 70s, there is a replacement wave coming up. We don't exactly know when, we don't exactly know how urgent it is. I think we are for sure that within the coming decades, a lot of equipment, including transformers, will need to be replaced. These days, we have a lot of new diagnostic and monitoring technology at our disposal. So we can monitor transformers more closely than we could before. And if there is a danger of a failure as a result of aging or a defect, we can more often see it coming than we could before. And finally, a trend which is recent in terms of of decades is that asset management decisions are no longer aimed at doing the best we can, but it's taking a risk-based decision, and I will come back to that. So the question I have addressed in this presentation is, how have these recent trends that I just mentioned, how have they influenced transformer asset management, and in particular transformer replacement decisions, and what kind of criteria come from that? Now, if you look at modern asset management, then many people will automatically say past 55, or since last week, ISO 55000. And the bottom line is that asset management has changed over the last decades. As I said, it's no longer doing the best we can. What we learned at university, at least what I learned at university, is what is the best thing you can do, what you can make, what you can maintain. But these days, decisions are taken from a risk perspective. We try to maintain balance between performance, cost, and risk given company business values. We all know that creating high performance is an easy job if money is no objective. And keeping the cost low is no problem if you don't demand high quality. But it's the balance between performance, cost and risk that is the challenge for the asset manager to accomplish. And in that background, PAS 55 was developed in 2004. It was renewed in 2008. And it was last week on January 10 that ISO 55000 was issued by, by the IEC. So now we have an asset management standard with not only publicly available specifications such as PAS 55, but a formal standard. Now, what does that mean? What kind of an impact does that have? It has changed the way we look at asset management organizations. We have these days an asset management model. We have asset management systems. So all kinds of activities and conditions that have to be fulfilled in order to have a good asset management system that fulfills the requirements of PAS 55. We work with risk management matrices. We have asset management processes introduced. I'm not going into much detail about that, but I want to take out a few items that are relevant in the framework of this presentation. If you look at an asset management or a risk-based decision, then it follows a path. And it starts with defining business values. If you do not know what is important to you, you can also not define the risks that you are, or the hazards that you are exposed to. So what utilities do these days is they formulate their business values. They have business values for reliability, for safety, for cost, for environment, for compliance to the regulator, and so on and so forth. And that is the framework of what they think is important. Then hazards are identified, and hazards are possibly risky situations. You don't know yet what is the probability or the impact, but you know that it's a possible danger. Once you have a hazard identified, you're going to analyze it. And analyze it, that means that you try to establish the probability of that hazard and the impact of that hazard. And the combination of that is called the risk. Now, in itself, it's not a decision. You have to define what degree of risk do I accept, and that is called risk appetite. And of course, you can for some time claim that your goal is to avoid risk, but risk cannot be avoided. It can only be controlled. It can be made smaller, or you can accept a higher risk, but risk avoidance is not, if you talk about risk avoidance, you don't understand the concept of risk. There is always a finite possibility, a finite probability of a hazard occurring. And you have to define what degree of risk is acceptable or not. And based on the risk, decisions are made, decisions are prioritized in terms of urgency, and they are prioritized in terms of risk reduction effectiveness. What measure gives me maximum risk reduction? On the right side of this sheet, you see some examples of those business values, and I took out one example, safety. And an example of a hazard when you talk about safety is, for example, the explosion of a transformer or a part of the transformer, which can cause a fire and which can produce toxic byproducts which are exposed to the public. So this is called a hazard, and the analysis will then have to expose what is the probability of this hazard to happen and what is the impact. And once you know that, then you can mitigate. And there are two ways to mitigate. One is you can prevent this hazard from happening. For example, by doing good maintenance, by applying monitoring, by replacing the transformer. You can also try to limit the impact. the consequence of this failure by protection, by introducing firewalls or pressure relief valves or taking safety measures. And the task of the asset manager is to make the right choice here. Now, why is this relevant? Let us look at transformer replacements, because intuitively we think that a transformer is replaced because it gets too old and the failure probability gets too high. Practice is that this is not the most important reason for replacement. So what other reasons are there? Let's first look at, do transformers actually reach the end of life? If you look at failure causes, we see that the most frequent causes of failure are tap changer failure and bushing failures. Could that be a reason to replace? Yes, it could, but tap changes and bushings can also be replaced. So this is not necessarily a reason to replace. We also see that only few failures are caused by external causes, such as short circuits or lightning strikes or transient overvoltages. It does happen, but those are not the dominant failure causes. And what we see is, if we look at transformers that are being replaced in practice, that, well, first of all, that end of life is not based on age. You can have a transformer of 30 years old that is in bad shape. You can also have a transformer of 60 years old that is in good shape. So age in itself is not a replacement criterion. If you want to replace it based on degradation due to lifetime, it should be based on the remaining life. How many useful, safe years can I still do with this transformer? If you look at the mechanisms cause a transformer to really reach the end of life, then it's only the winding paper insulation that shows a degradation that cannot be repaired, that is irreversible. Bushings can be replaced, tap changers can be replaced, valves can be replaced, but winding paper insulation can hardly be replaced. Of course, you can rewind the transformer. Economically, that is hardly ever a good option. So you might say that only insulating winding paper degradation is an irreversible mechanism that would lead to the end of life. That is why we pay so much attention to it when looking at the condition and the lifetime, remaining life of a transformer. That's why we use the loading guide, why we use further analysis as an experimental and diagnostic tool, and why we are interested in statistical analysis. So if you really look at the end of life of a transformer, then I say it's determined by the paper insulation degradation. Whether it is end of life also depends on the failure probability. If you look at here, then that in fact you don't have an end of life in terms of a specific time at which the transformer fails. You cannot predict with an accuracy of 1 month when the transformer will fail. What we have, in fact, is an increasing failure probability in time. So how do you then define the end of life? You could say mathematically, when the failure probability is 50%, that I call that end of life. But no utility will accept a failure probability of 50%. So they will accept a much lower probability, and they will, for example, say if it reaches 5% or so, I call that end of life. I call that time to replace. So end of life is actually a failure probability versus time. But then again, if you look in practice, the end of life, however you define it, is hardly ever reached. Mostly it's replaced before the end of life is reached. So that poses the question, why do we then replace transformers? What are the reasons for replacements? And then you see a top unacceptability of failure probability. This is what I just mentioned. If you don't accept a failure probability of, let's say, 5%, then this can be a reason for replacement. But there are more reasons. A transformer can lose its functionality. For example, well, what is the functionality of a transformer? It's to transform power from one voltage to another and to deliver power. And it situation is often occurring that a transformer which is technically in good condition is not able anymore to deliver sufficient power, or is not able anymore to comply with government regulations or safety, health and environment regulations, because the demands have changed. For example, the power rating of the grid has changed and the transformer cannot transmit sufficient power anymore, or because environmental requirements have changed. So the transformer didn't change, but the environment changed, and this can be a result of the transformer losing its functionality. That is regularly a reason for replacement. Another reason for replacement, which you see more often at older transformers, is that a transformer can no longer be maintained. For example, because spare parts are no longer available, or because technicians within the company or technicians at a contractor do not have sufficient knowledge anymore of this old type of transformer, or they don't have the capacity to maintain it, or they don't want to maintain it because it's not sufficient volume for a profitable business. Another reason, another argument important here is that if you have a high diversity of transformers, maintenance gets complicated, gets less effective. The more uniformity you have, the more efficient you can organize your maintenance and your knowledge and competence. So transformer losing maintainability is another reason for replacements. Also, transformers may have operational issues. For example, transformers have losses. We know transformers have losses. They have always had losses, but these days new transformers have lower losses than the old transformers. And they may be somewhat more expensive, but in the long run you will have less operational costs. So at some point you may argue that replacing a transformer by a low-loss alternative is an economically viable solution. This sometimes also is a reason for transformer replacements. So once you know this, once you know that there are a number of reasons for transformers to be replaced, actually all those reasons are related to a risk. If I go back to the previous page, then losing functionality causes a risk because it can limit the capacity of a grid. Losing maintainability is a risk because it can jeopardize the reliability of the grid. And transformer operational issues such as losses of transformers can cause unacceptable losses and costs. So in all these cases, whether it's failure or another reason, there is a risk. And if you talk about risks and risk management, then you see, I see that the sheet has a little bit deformed, but you can read it anyway. Risk management, there are different phases that you can recognize. The first phase is the risk analysis, and risk analysis means that you, for each hazard, you try to estimate the probability and the impact. So it gives you the basic data for your risk assessment. The risk assessment itself is first try to understand the problem. What is the probability, what is the impact, but also what is the environment, what is the grid, what are the options. You look at scenarios. Sometimes you cannot predict the future and you use scenarios, for example, worst case, best case, realistic case, in order to get some basis for your analysis. You can look at different alternatives. What if I have a problem with a transformer? What are the possible mitigation measures that I could take? And what kind of constraints should I take into account? Constraints could be that you are in a certain grid and you cannot change the requirements of the grid, so this is a constraint. The constraint can also be that I have a certain budget and my solution has to fit within the budget. You also try to establish whatever mitigation measure I take, what is the objective of that measure? What does it cost? But also, what kind of life expectancy do I expect if I have used this mitigation measure? If the life expectancy is too low and I change something, I change my maintenance or whatever, I need to know what gain do I get from this measure? What is the objective of this measure? And then finally, you take a decision. Once you have taken this decision, then you can start the risk treatment. And actually, because each utility has a number of hazards, you have a number of risk assessments. So you have a whole portfolio of problems that you need to deal with. So the first thing to do is to prioritize. You can prioritize on urgency. You can prioritize on risk. You can prioritize also on the effectiveness of measures. So there has to be some prioritization, a selection of the certain measures and perhaps postponement of other measures, and then is the planning and execution. Those are the regular phases of risk management. And what kind of measures could you take? Well, this is a very general picture. How can you mitigate a risk? You can try to prevent it. Let me use this arrow here. You can try to prevent it. Smoke detector is a well-known example. You can try to repress it. That means that you try to suppress it in an early stage before it has caused too much damage. In a later stage, well, you can do the firefighting if it has really become too worse. You have not been able to repress it. You can correct. You can be prepared, making emergency plans, making escape routes and all that. You can also transfer the risk. That means that you pay for an insurance, or you can simply accept it and say, well, I accept that there is a certain risk, and if it happens, it happens, and I take care of it, and I am trying to prevent it, and I'm not trying to insure it, which is a way of dealing with it. Now let us look at transformers and see what kind of mitigation options we do have there. First, if you have functional limitations, you can try to adjust functional characteristics. So actually what I'm going through now is a list of mitigating measures that you can use if you suspect that the transformer has some problem related to its functionality or to its lifetime. And this will show you that there are alternatives to replacements. And one of the alternatives, for example, if your transformer is not able to function properly, for example, because the power rating, the grid has changed, well, you could increase the power rating of the transformer by applying enhanced cooling. If the problem would be that you produce too much noise according to modern standards, then you could apply acoustic insulation. If the problem is that you are not allowed to spill PCB containing oil in the environment, you could try to clean the oil or replace the oil or contain the oil. Those are all examples of problems with transformers which may be technically in very fine condition but have a functional limitation. If there is some danger of some hazard that is related to a possible risk or a possible defect, then you can replace the transformer, or you can intensify monitoring and intensify maintenance. What you then try is to accept the fact that the defect or the failure will come at some time, but by doing maintenance, you can see it coming and you can define the right time to replace it. And by doing proper maintenance, you can slow down the degradation process. You can postpone the moment at which the transformer needs to be replaced. So you could, for example, use higher maintenance frequencies or additional maintenance activities, do some additional measurements, some additional diagnostics. You could apply transformer monitoring, which is continuously doing measurements on the transformer in order to develop the behavior in time. And another thing you can do is use health indexing tools. One of the problems of today's asset manager is that there is a wealth of data on the grid, on the transformers. And the problem is to make decisions based on that. The problem is to make decisions, sorry, I was disturbed for a moment, to make decisions based on this wealth of data. And for that, these days we have the availability of health index tools which transform the many data on equipment that you have to decision criteria. And this is another way of being able to monitor transformers more closely by having a good decision-taking software tool. What other mitigation options do you have? Well, refurbishment and lifetime extension. Actually, this is the same if a transformer has subcomponents that are not functioning properly, but the transformer as a whole is not yet jeopardized. You can replace the suspect parts like a bushing or a tap changer and thereby extend the life again. You can also change operation and maintenance policy and practice, which is not often that, well, if in case of intensification of maintenance, it sounds like the thing you could do with old equipment. Of course, you have to take into account that you will spend more time and money on maintenance, and at some point you may decide that the cost of maintenance are so high that it's better to buy new equipment. But another possibility that is sometimes used as an intermediate solution is to control load. If, for example, a transformer is aging and you know that it can no longer sustain its nominal load for a longer period of time, you can control the load until you're able to replace the transformer. So those are all mitigating measures that can be used instead of replacement, but in the end, at some time, replacements will have to occur. For replacement, we know for distribution transformers that the end of life is seldomly a replacement criterion on its own. It's usually combined with other aspects as well. And those other aspects include lack of spare parts, lack of service, losses in the transformer, inability to meet requirements. So usually it's not only age or it's not only the end of life which is nearing, that is the replacement criterion. A recent criterion that has come up is that it can also be used as an instrument to spread costs and manpower. And this is especially related to the upcoming replacement wave. If many transformers have to be replaced in a short period of time, that will be a huge investment, and it will also consume a lot of manpower. And it's even a question whether all the transformer manufacturers can supply sufficient transformers to replace vast volumes of it in practice. So what you now sometimes see is if replacement waves are foreseen, then preventive replacements of the oldest or the worst transformers can be an instrument to spread the wave, to spread the replacements over a larger period of time, to spread the costs and to spread the manpower effort. This is in more and more cases seen these days, that the replacement wave influences the rate at which transformers are being replaced. Now, we have a lot of options, and choosing from the options is a decision-making process. And based on or influenced by modern risk-based asset management and inspired by PAS 55, ISO 55000, decision-making procedures have been developed. And here you see some examples. On the left side you see an example of a suspected end of life. So the question is this transformer near the end of life, and what should I do? And then the first thing, and all the steps are you have already seen in the first part of the presentation, you first try to quantify the problem. What is the failure probability? What is the impact? Next step is, what are the opportunities for improvement? It could be lifetime extension, it could be replacement. And if it is lifetime extension, well, there could be several options. It could be a minor refurbishment, it can be a major overhaul. There are different options. And for all of the options, we look at the costs and the benefit. How much does it cost to do this exercise, but also how much gain do I have? How many more years do I have? And do I need to have additional maintenance during those years or not? So this is a cost-benefit analysis, and in the end, based on that, a decision is being made. You see this kind of decision making for all kinds of asset management decisions. On the left side is the example of suspected end of life, but you can also use the same kind of decision making for capacity bottlenecks. Do I have a capacity bottleneck? What is the congestion probability? What is the impact? What are the opportunities for improvement? And so on and so forth. So this is sort of a standard asset management decision making process. And here you see the steps in such decision-making process. As I said earlier, it starts with defining business values and keeping an inventory of possible risks, of hazards. You analyze the risk, you prioritize them, and then you have a first decision which is on priorities. But that doesn't tell you all. Before you can make a decision, you first have to look at reduction measures. Sometimes you have to look at different scenarios before you can make a decision. And then you have a decision on one possible risk. And if you have more possible risks, you will have a portfolio of risks which has to be managed, which has to be prioritized and has to be budgeted. And then you have a planning and an execution. I'm treating this on a rather high level, but if you want a more detailed treatment, then there is another publication of the European Copper Institute issued last year where you can in more detail see how to go through a transformer replacement decision process. So in this decision-making process, the key criteria are failure probability, impact, but also risk profile and risk appetite. So risk profile means what is the probability and impact of this failure, but what is also important is what risk do I accept? What is my risk appetite? And then you look at different alternatives and look at the effectiveness of different alternatives. And you look at the cost and return on investment of the different alternatives. So in fact, these are the replacement criteria. But of course, this is not very satisfying for you as an audience because it only tells you how to go through the process. So I will go one step further. Well, what I also say on this page is that except for the regular key criteria in any decision process, for aging transformer population there is another constraint which I mentioned earlier, and that is to control the replacement wave. How do I prevent that investments are too much concentrated in time, that manpower effort is too much concentrated in time, and that I do not overstretch the production capacity of manufacturers. So let us go to some conclusions, and the first ones will be rather generic, and then they will more and more be related to transformer. First of all, transformer replacement is an asset management decision process. And this decision-taking process is governed by business values, by risk evaluation, risk appetite, urgency, risk reduction capability, and so on. All the things that I mentioned before. And for that, there is a decision process in place, and there is what we call a risk matrix in which utilities define for each business value what kind of probability classes they use, what kind of impact classes they use, and whether or not to accept, is this an unacceptable risk or a high risk, a medium risk, a low risk, or a negligible risk. So one conclusion is that this is the process that is governing replacement decisions. Or can we say more to that is more specific to a transformer? Yes, we can. Some other conclusions. Transformer age in itself is not a replacement criterion, because some old transformers may be in good shape and some young transformers may be in bad shape. It's not the age, it's the end of life that is the replacement criterion. But even then, end of life is hardly ever reached. End of life is governed by loss of life, and loss of life is depending on load, is depending on temperature. We can try to establish that. In practice, it's hardly ever the reason for replacements. Common reasons and common criteria include transformers losing functionality, transformers losing maintainability, and other operational issues such as losses. One of the reasons why transformers are not always replaced is because there are also alternatives to replacements. For example, adjusting functional characteristics, intensifying monitoring and maintenance, refurbishment, lifetime extension, and adjusting the operation and maintenance policy and practice. So, looking to high power and distribution transformers, transformers in general, you could say that replacement is depending on the lifetime consumed, not on age, but on the remaining life. There are alternatives to replacements, and I have shown them on the previous page. And they are often attractive for high power transformers because they require some investment. If you apply monitoring, then you have to make an investment, not only in equipment, but also in the people who have to analyze all the data, or in a computer system that has to analyze all the data. So replacement alternatives come at a cost, and for high power transformers, these costs are often small compared to the value of the transformer. So if high power transformers, let's say in transmission grids, often such techniques can be afforded. However, if you look at distribution transformers, you may say that they are often regarded as commodities. They are relatively inexpensive, they are deliverable off stock, and if you try to keep it alive longer by, for example, using maintenance or intensify maintenance or applying monitoring, then this may be more expensive than replacing the transformer right away. So for distribution transformers, common practice is that they are quite easily replaced because all means to keep them alive longer are too expensive. So if you want alternatives to transformer replacement, they should be low cost, they should be effective, efficient, standardized. You cannot have a tailor-made solution for each individual distribution transformer that will make it too expensive as compared to the price and the availability of these transformers. Now that brings me to the last conclusion. If you talk about distribution transformer alternatives, and then I mean alternatives for replacements, they are there, but they have to be low cost and they have to be very effective. So, and if you don't have it low cost and effective, efficient, then the common policy will be to replace them as soon as there is a reason to do so. And low cost and effective and efficient means that it only works if those monitoring devices are integrated as low-cost commodities. They should not really increase the price of a transformer. They should almost have no effect on the price of the transformer. And you're not going to monitor an individual distribution transformer. At least that is not a very cost-effective way. If you monitor distribution transformers, it needs to be on a fleet scale. You monitor a whole population in such a way that as soon as one transformer out of this population reaches a danger limit, you can identify it and replace it. So this calls for effective condition assessment routines in your maintenance program, and it calls for effective health indexing tools where you just automatically put in monitoring data or maintenance data, and it tells you which part of the grid you should take action in. What distribution substation is suspect, what transformer is suspect. I show here on the right-hand side a graph from one of our health indexing tools where you see the number of assets in different risk areas, risk classes. So if you think of distribution alternative replacement, it has to be low cost, it has to be effective. If not, then the most economically viable solution is to replace distribution transformers. And that concludes my presentation. So I would like to, first of all, thank you for your attention, give the floor back to the facilitator, Fernando, and there will be time for answering some questions.
Okay, thank you very much, Jos, for this great lesson. So let's, I remind you just to click on participant view for the Q&A pod, and then I will be sending there coming questions. So here we invite the audience to please submit all the questions you might have. So we have already some of them been arrived. So we have a first question by Javier Galvan. So is there any criteria to consider the additional operating costs due to energy losses, energy efficiency, as a decision factor to replace a transformer?
Well, the answer is yes, but like the rest of my presentation, it is not just a simple criteria, it's an evaluation. What you would have to do in that case is do sort of a life cost analysis, where you look at the cost over a longer period of time, and you include additional operating costs due to the losses accumulated over time, and you compare that to the additional cost that you have to make in replacing the transformer with a low loss alternative. So in fact, you look at two alternatives. One alternative is as usual. Second alternative is replace the transformer by a low loss alternative. And you look at all the costs, investments and operational costs over a longer period of time, and you compare the two, and then you have a business case.
Okay, good, thank you. I think there is another question very close to this one, so it's probably already answered. What's the impact of energy efficiency on replacement criteria? So I believe you already provided an answer by saying that, well, it will basically depend on case-by-case basis. It's needed to be estimated what's the cost of losses cumulative over the lifetime. But well, if you have any views or any practical experience on whether this is usually the case, that
well, actually the answer is almost the same as for the previous question, and the reason why it's often being regarded as a difficult decision is because you have to compare investments with operational costs. And you can only do that if you do it by sort of a life cycle analysis, where you can incorporate both the capital expenses and the operational expenses in one evaluation, and then you have an comparison. So it calls for a life cycle analysis.
Okay, good. So let me Okay, sorry. I believe we have here two questions at the time. So we have the first one. In the case that transformer is working partial load, which is considerably lower than its capacity, is this situation a factor that could justify a replacement? So the fact of being working at partial loads?
No, I don't know if I understand the question correctly. Let me try to rephrase it. If the transformer is at 50% of its nominal load, then there is no reason to replace it. It actually, with a low load, it will live a lot longer than with a high load. But perhaps what Javier means is that if a transformer cannot carry more than part of its nominal load, if that is the case, then that is a reason to consider replacement, because in that case something is wrong in the transformer. And if a transformer is not able to operate above a certain percentage of its nominal power, then something is really messed up in the transformer, which means that it's consuming its lifetime in a rapid rate. And then I would say that replacement is justified, yes.
Okay, good. We have another question from Mike Scotland. In your experience, Jos, what is the typical service life of a distribution transformer in Europe? In the US, we always used 32 years as the average life, but your graph showed about 10 years as half-life.
Yes. Mike, I understand the misunderstanding. We are not using 10 years as a half-life. What I showed was a picture of the failure probability versus time for an existing transformer. In this case, the transformer already had an age of 40 years. So it was telling that within the next 10 years, so at the age of 50 years, it would reach 50% failure probability. So I know, I understand the misunderstanding. What in Europe we usually use what is used as average age is in the order of 40 years. And actually I'm surprised that in the US it's only 32 years on the average, because I know in the United States you don't want to replace equipment unless it's really necessary. So is this, my counter question, I don't know if that's possible, is this really a replacement age or is it considered as some average value for calculations? Okay. I don't know if Mike can answer that, but...
Yeah, we invite Mike to probably to submit a complementary comment that we could address okay. in the coming minutes.
Okay.
Okay, good. So there is another question on the possibility to have the presentation. So it's available in the link indicated in the right posts, either in the speaker or contacts references, and the link on today's presentation or recording. Good. So Mike is now providing some further feedback. So let me just forward this and that, and let me read it.
Okay, yes.
So no, it was an average value used for calculations in the U.S. Department of Energy's regulatory analysis for setting efficiency standards on distribution transformers in 2007. Thanks, Jos. That was very helpful to know.
Yeah. Okay. Yes, I understand, because in that case you use it as to calculate the write-off of our equipment, and if you can write it off in 32 years, that is reasonable. If you look at the common practical ages, then we have transformers up to 60, 70 years of age which are still functioning well. but which may be replaced for other reasons than technical condition. And I'd say the average that we calculate with is about 40. The average in practice will be somewhat higher.
Good. We have another question from Robbie. What monitoring system do you advise for distribution transformers? Do you advise to take oil samples of hermetic sealed transformers?
Well, in general, oil analysis is a perfect way to start monitoring, to start a condition assessment. But for many distribution transformers, especially for hermetically sealed transformers, it's not possible. And even if the transformer is not hermetically sealed, it's too expensive to do it as a standard routine on all transformers. So if you look at monitoring, you could, for example, for the distribution transformers, consider partial discharge monitoring, temperature monitoring, load monitoring. Often, if you know load and temperature, you know if something is wrong. What we often do when we do scans of substations, for example, is that we then take portable partial discharge equipment to see if there is partial discharge activity. You can use infrared thermography for scanning, but if you really think about monitoring, I would say that first of all, temperature and current, or temperature and power, would be the first ones, and you could think of partial discharge monitoring as well for, let's say, strategic substations, for example.
Okay, thank you very much for this answer. We have another question about energy losses. Are the energy losses higher in transformers that operate at partial loads?
That's a good question. Well, the energy losses are divided between the iron losses in the core and the copper losses in the windings. My first intuitive answer would be no, it doesn't matter very much what is the load. But in order to substantiate it, I would have to go back to the formulas that describe energy losses, and I don't have them at the top of my head. So I'd say no, but I would have to confirm that with a calculation. But if you look at in handbooks on standard formulas on transformer losses, and you look at iron, you separate iron and copper losses, then you will find an answer pretty soon. If you were here at my table, we could calculate it together pretty quickly, but that's not the case.
Okay, thank you, George. No problem. Actually, we can very well publish afterwards such formula in the web page, so this will be available for everybody to address this question. So no problem. So just forward to me, and I will upload in the same web page.
Yes.
Excellent.
Fine. Yep.
Okay. So I believe now there are no remaining questions. So thank you very much, Jos, for this excellent lesson we all have. Good to everybody for joining today, for your attention and your interesting questions. And now, Jos, I give you the floor to close the session.
Okay, well, thank you very much, Fernando, and thank you to all the participants that have taken the trouble of connecting and listening to the story and taking part of the discussion. It's very helpful for me. If you have any remaining questions, then the presentation will be available through the European Copper Institute. There will be my email address on it. So if you would like any further discussion, then please don't hesitate to contact me. So I would like to thank you, listeners. I also would like to thank the European Copper Institute for inviting me to present this part of the work to the audience. So thank you very much, and I hope to see you at some occasion.
You're welcome. Thank you. Goodbye for now.